Welcome, my friends! In the previous video, we discussed the multiplication rule of counting and permutations. In this video, we will be introducing combinations and comparing permutations and combinations. I highly recommend that you watch my previous video first if you haven't already, as I will be building off the material I introduced there. As a reminder, counting techniques help us determine the number of ways some event can happen. We will begin by comparing permutations and combinations, as they're quite similar. First, remember that in order to use a permutation, you must be sampling without replacement, and the order that the objects are chosen must matter. For combinations, we still must sample without replacement, but now the order that the objects are chosen does not matter, or is not something that we're interested in. The most difficult part for most students is determining whether or not order matters, as what we mean by order can be slightly different depending on the situation. For example, we looked at a problem in the previous video where we were interested in the number of ways first, second, and third place could be awarded from 8 runners in the 100-meter dash. We used a permutation to solve this problem because we cared not only which runners placed in the top 3, but also the order or place that they came in, first, second, or third. If I'm going on a trip across the country and I have 5 friends, but I can only ask 2 of them to join me on the trip, I would use a combination to count the number of ways there are to choose those 2 friends. I only care which 2 friends will join me for the trip, and the order that I choose them makes no difference. With both permutations and combinations, we have n objects, which can be people, balls from an urn, cards, or any other object of interest, and then you must select r of those objects, where r is some number less than or equal to n. The permutation tells you how many ordered ways there are to choose r objects, and the combination tells you how many unordered ways there are to choose r objects. The combination of n choose r can be written at least 4 different ways. I prefer this notation with parentheses, which is typically how you will see it in more advanced probability textbooks, but I will be using the notation NCR to be consistent with our permutation notation and with the TI calculator. The combination of n choose r can be found by taking the permutation of n choose r and dividing by r factorial, or by using this formula, n factorial divided by r factorial times n minus r factorial. Here is my disclaimer. I don't like to use formulas just for the sake of using formulas. I only like to use and teach formulas that are helpful for understanding the topic at hand, and this formula is generally not all that useful for understanding what a combination is. It's like a black box. You might as well just use a computer to find the answer. Nevertheless, many teachers use it, and it's sometimes helpful to be familiar with, so I will still show you how to use this formula. This formula, on the other hand, is very useful for understanding combinations, and it's the one that I like to focus on. It shows that there is a relationship between permutations and combinations. Notably, that the combination is just the permutation divided by the number of ways there are to arrange the objects that you're choosing, r factorial. We will explore what this means when we look at an applied example momentarily. Since r factorial is at least 1, combinations should be less than or equal to a permutation calculated using the same values for n and r. Let's try to calculate a combination using both formulas. Consider the combination of 7 choose 3. n equals 7 and r equals 3. Using the first formula, we have the permutation of 7 choose 3 divided by r factorial, which is just 3 factorial. Remember that for the permutation, start with the number n, in this case 7, and then multiply 3 numbers together, decreasing by 1 each time. So we have 7 times 6 times 5. Then we divide by 3 factorial, which is just 3 times 2 times 1. This simplifies to 35. Using the other formula, we have n factorial, which is 7 factorial, divided by r factorial, or 3 factorial, times n minus r, or 7 minus 3 factorial. This simplifies to 7 factorial divided by 3 factorial times 4 factorial. 7 factorial divided by 3 factorial times 4 factorial is just 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 4 times 3 times 2 times 1, which simplifies to 35 again, the same answer we got using the first formula. Let's look at how you might type in the second formula into your calculator. Once you have simplified the combination to this point with just factorials, that might be a good time to go to your calculator. I'm using the TI-84 calculator, but the process should be similar on most calculators. We have 7 factorial divided by 3 factorial times 4 factorial. To type this in, first type 7 and then press the factorial key. On this calculator, I need to press the math key, then arrow left once to get to probability, and then option 4 is the factorial key. Next, press the division key. Now open parentheses and type 3. Then go back into math, arrow left to get to probability, choose option 4 to get that factorial symbol again. Then type 4, go back into math, arrow left to probability, option 4 to get one more factorial. Notice that I didn't need to enter a multiplication sign between the two factorials. The calculator knows you want to multiply 3 and 4 factorial together. Close the parentheses and press enter. You should get 35. Alternatively, you can skip this process altogether and go right to calculating the combination of 7 choose 3 using the calculator's built-in function. To do that, first type in n, which is 7, then press math, arrow left to probability, and select option 3, NCR. Then type r, which is equal to 3, and press enter. You should get 35. Now, it's really easy to lose sight of what these calculations mean without applied problems, so let's look at some real-life examples. Suppose the manager of a company needs to hire 3 employees out of 5 applicants. Consider 2 scenarios. In scenario A, the 3 positions are different. One position is a production line operator, one is a night shift manager, and one is a day shift manager. In scenario B, all 3 positions are identical. They are production line operators. How many ways are there to hire the 3 employees in each scenario? Recall the conditions needed for permutations and combinations. In each case, we must be sampling without replacement, meaning that once an individual has been chosen, they cannot be chosen again. This is true in both scenarios. Presumably, an applicant can only be hired for 1 out of the 3 positions. The second condition, relating to order, is where the scenarios will differ. In scenario A, order does matter because the positions are different. The first, second, and third positions all have different titles, production line operator and day or night shift manager. So we don't just care which 3 people get hired, we also care which positions they get hired for. This makes a permutation appropriate here, as order matters. In scenario B, the positions are identical, so it doesn't matter which order the positions are selected, as they're all the same. All we care about is which 3 applicants get hired. This makes a combination appropriate here, as order doesn't matter. N is equal to 5, and R is equal to 3, since there are 5 applicants and only 3 positions. For scenario A, the permutation of 5 choose 3 starts with N, or 5, and multiplies 3 numbers together, decreasing by 1 each time. So that's 5 times 4 times 3, which is equal to 60. There are 60 ways to hire 3 applicants for unique positions. For scenario B, we take the permutation of 5 choose 3 and divide by r factorial, which is 3 factorial. This becomes 5 times 4 times 3 divided by 3 times 2 times 1, which simplifies to 60 divided by 6, or 10. There are 10 ways to hire 3 identical positions from a group of 5 employees. To make this example even more concrete, suppose we have the names of the 5 applicants. They are Olivia, Liam, Noah, Emma, and Ava. We calculated that there are 60 permutations, or ways to assign 3 of these individuals to the positions of production line operator and day and night shift managers. One permutation might be Olivia, Liam, and Noah in these 3 positions. But since the positions are each different, switching the order around results in a different outcome. So Olivia, Noah, Liam is a different outcome, which is different yet from Liam, Olivia, Noah. Even though these outcomes all have the same 3 people, they are considered different if the order matters. In all, there are 6 possible reorderings of the same 3 people. How could you know that there were 6 without listing them all out? Well, we are choosing 3 people, so r is equal to 3. And 3 factorial is 3 times 2 times 1, or 6. Remember that 3 factorial tells us the number of ways there are to arrange 3 objects. Here we have all 6 arrangements of those 3 objects, which in our case are applicants who received a job. A combination, on the other hand, treats all 6 of these outcomes as the same. Order doesn't matter. All that matters is that Olivia, Liam, and Noah were chosen, not their order. In our example, if the positions are all production line operators, these 6 permutations represent just one outcome, or one combination. It should start to make sense now why the combination is just the permutation divided by r factorial, because r factorial is the number of ways that the objects you are choosing can be ordered. In this case, for every 6 permutations, there is one combination, which is why we divide by 6, or 3 factorial, in the formula. In this spreadsheet, I have all 60 permutations and all 10 combinations. Here's the first one that we looked at, Olivia, Liam, and Noah, which is one combination. But it can be arranged in 6 ways if we care about their specific positions or their order. Here we have another one, which is Olivia, Liam, and Emma, which can also be arranged in 6 ways. This continues down until we get to 60 permutations and 10 combinations, the numbers that we calculated earlier. The hope is that this helps you grasp the difference between what permutations and combinations are doing, which can also help you determine which counting technique is appropriate in future problems. Alright, my friends, that wraps up our introduction to combinations and a comparison to permutations. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.